Okay, welcome everyone. So before we start, let me just say welcome to the guests that we have today. We have again visitors from high school who want to figure out how it is at the university. And as I always say, I'm trying not to scare you away. I try my best. Yeah, this is actually quite a nice lecture to visit today, because we are kind of at an intersection. We finished up last time a part on perspective projection methods, and today we're going to switch to ray tracing. And because this is kind of a different thing, I think, and also because I bother you, now I'm talking to the others, not the high school students. Now because I'm bothering you a lot with the theory and the mathematics here in this course. I think this is a nice opportunity also to look at some graphics again, and some real graphics, and what better place is there to look at the latest and greatest graphics than at Pixar movies. So let's just have a quick look at the latest movie or upcoming movie from them. All right, so of course, what you've seen now goes way beyond what we cover in this course. But I hope that the next time you're watching a movie like this, you're not just enjoying the movie, but you're also admiring the nice computer graphics there. And maybe if you see something like a marble or so, that you will remember then, okay, this might have been done with Perline noise techniques. So of course we're not covering all the stuff that you need to do this kind of really advanced graphics here, but the basic principles that they use are exactly the same as what we are doing here. So you made the very first step to become the next great Pixar artist. But of course most of you, I think, are also are mostly here because of the games, because this is a game-focused program. So let's also have a quick look at the related computer game. Good. Okay, so of course I'm not doing this just to entertain you, because my job is not to entertain you but to educate you. And of course what you've seen here, if you compare the two clips, the movie and the computer game, then if you look at the computer game compared to the movie, then the graphics actually look quite crappy, because I have some examples here. This is especially a scene where you see it with the fight scene with the bear. You see here how detailed the grass and the bear claws are modeled compared to what you have actually in the game. I think if they would make a movie like that, no one would want to see it. But of course, I think you also kind of understand why we have this, because the point is that a movie, you pre-render the movie once and then you make a copy of it and send it to the movie theater, so you don't have to do any calculation while you're watching the movie. Whereas with a computer game, where you interactively control the game and your actions influence, of course, the graphics, you have to update it in real time, so you have to do a lot of calculations in real time. So the speed is really the important issue here, which is why the graphics in computer games are, of course, not as sophisticated usually as they are in animated movies, which is also, to come back now more to the background of the course, why here you use usually the hardware pipeline that we discussed, the graphics pipeline supported by the hardware, whereas at Pixar they usually have a software implementation, or a lot of the stuff that they have is not from the hardware, but is not the hardware pipeline that you use when you implement the game, but is also implemented in a software pipeline, because a software pipeline, of course, gives you more freedom also to do certain kinds of modeling that you cannot do because the hardware just doesn't support it. On the other hand, of course, the software pipeline takes much longer because it is not hardware supported. And that, of course, is the reason why why I brought this little movie clip and this little introduction here, because that makes a nice transition to the next step, which is then ray tracing, because ray tracing is usually considered to produce even more realistic images. So if you want to really have photorealistic images, very often people use ray tracing techniques. Now, just a few words, since I know that most of you are game students, so a lot of people think then, okay, if ray tracing is not used in games, why should I care about it? I mean, first of all, those techniques approach each other more and more, so there are also there is a trend towards real-time ray tracing techniques, so it might show up in, or you might use it in computer games in the future. Also, of course, in general, if you study computer science, you should have an overview of the whole field, and ray tracing is one of the major basic methods in computer graphics. And also, of course, many of the techniques that we use for ray tracing are quite similar to the techniques that we use for projective methods, or a few new techniques that we will learn for ray tracing, or in context with ray tracing, might also be useful for projective methods. So, but also because the techniques are so similar, of course, it is also a good repetition for you. In fact, a lot of the stuff that I will do today are things that you should already know or should already understand how it is done based on what you have learned so far. So we'll do a lot of repetition today also, but I mean 2 weeks before an exam, that's probably also not such a bad idea. Good. Speaking of repetition, we start. I just copied the lectures from the slides, a couple of slides from the very first lecture. So this was the one of the very first slides where I talked about the basic techniques in graphics in image generation, which are modeling and rendering. And then we talked a lot about these projective methods, where we said we model an object by, for example, a triangle by the 3 vertices. Then we project it towards the screen, and then we put some color on it, so we make a so-called shading. And for example, at the beginning, I also asked you what happens if you have more triangles that are mapped onto the same pixel. And then, of course, you knew that you already knew then that you only draw the one that is closest to you. But now, hopefully, you also know that how to do that, namely with a set buffer, for example. Good. And also in the practicals, you did a lot of work on this, but we also talked a little bit about something that you didn't do, which is the ray tracing, which is a second major approach in computer graphics to create images. And maybe you remember it. The idea was for the projective methods, we looked at all the objects and then we projected them towards the viewing position, or the virtual camera position, or our eye position E. And then we said if there is an object here and I project it here, it is presented on the screen at this position where in the direction of the object towards the eye intersects with this area here. Now for ray tracing, we just go the opposite way. We say, of course, okay, if an object that is projected towards the eye is the one that I'm showing here, I can also go the other way. I can say if I'm looking from my camera position towards this pixel, then of course the point that I'm drawing here, or the color that I'm drawing here, is exactly the color that I see if I follow this line, or if I follow this ray, hence the name ray tracing. If I follow this ray and then draw the color of the first object that I hit here. And of course, if I have then here my normal vector, I can do a light calculation and then see what light source illuminates this point here. But also, of course, this object can hit another object where the light reflects again until I hit, for example, a light source at some point. So we have to make it really realistically, we do recursively follow this ray until we hit a light source, and then we know the concrete light conditions, and we know all the other conditions that influence the light at this particular point, and then we draw that point on the screen. And it's exactly this recursive following of the ray that makes these ray tracing images usually more realistic than with the software, with the projective methods. Although, like I said, those approaches are coming closer and closer together. So, for example, the images that you saw at the beginning from the Pixar movie, they look really realistic. You cannot really just say by the image that was done by ray tracing or that was done by a software pipeline, whereas if you compare the video game with the movie, then you can clearly say where the difference is. So, yeah. So here are a few examples that I already showed you before, and like I said also earlier, that before we had this gaming focus, we had ray tracing as practical assignments. So these are some examples from the results that we had then. And yeah, So, but now then we switched in the practice to the projective method, but I also already motivated why it still makes sense to look into the ray tracing. And this is like a summary that summarizes the major difference between it. For the projective methods, you have an object-based rendering. That is, you go through all the objects and project them onto the screen. Whereas for ray tracing, you have a pixel-based rendering where you go through all the pixels on the screen and then look if or what objects they are hitting. And so you see here that obviously there will be a lot of similar things in both approaches. So for example, texture mapping is an approach that is also used in ray tracing. Also, shading is the same approaches are used usually for shading, or similar approaches are used for shading in relation to ray tracing than we use for projective methods. In fact, the simplified shading model that we had at the very beginning was actually in the book from the chapter about ray tracing. But you also see some differences. So, for example, and also, of course, the similarities are for the projective methods. You could also, of course, do this recursive following of the rays to have all the reflections in a room considered, but it would be much more effort, and it would be in the ray tracing. It is kind of indirectly already implicitly the whole procedure is per default made in a way that this recursive following of the light and the consideration of the light is kind of implicitly integrated in the whole procedure, which makes it a lot easier. But you also see, for example, that there are certain things because we have a different principle here, a different approach here that we don't need in ray tracing that we have in the projective method. So, for example, we don't need a hidden surface removal or a set buffer because we're going from the other direction. So we're not going through the objects, but we're going towards the first object. So we already know what the first object is, so we don't have to treat this specially. Also, we don't have to do a perspective projection because we're directly going in the opposite of the perspective direction. Now, in terms of performance for the ray tracing, like I said, we have to go through each pixel, whereas with the projective methods, we have to go through each object, which, if you think about very complex models with thousands of triangles and having a lot of these models, then of course is also not very efficient. But the point is, so it might seem first that ray tracing should actually be faster because you're just going by the number of pixels, which is fixed. Whereas if you have a very large scene with a lot of models, you have a lot of triangles, so you can also have a lot of processing. But the point is, because of this recursion of the ray tracing, you have the numbers of pixels times the numbers of models or objects that you have, and that is of course this recursive step which makes the images more realistic but also makes the approach much slower. Good. So let's go through the details, the kind of the technique we need behind it. So this is a very simplified first algorithm, which actually doesn't even consider the recursion, but this is just the very basic thing that you need for ray tracing, which is a loop over each pixel, and then for each pixel we shoot a ray towards that pixel from the eye position, and then we determine the first object that we have. We get the color on that object, and then we draw that color on the screen. So this is the very basic thing we have to do for a ray tracing algorithm. And of course, so the first thing we have to specify is, if we want to implement that, is how we represent a ray. And this is the part now where the whole repetition from previous lectures come in, because a ray is of course nothing else than a line or a cut-off line that starts at a certain position and then goes in a certain direction. And this certain position is of course our eye vector, and the direction is the vector from our eye towards the screen. So if we use for this a parametric line equation, we can very easily write this down and model this by saying our support vector is our eye. So you remember, I hope you remember, the parametric linear equation was defined by a support vector, which gives you a position on the line, and a direction vector, which is a vector on the line, which gives you the direction of the line. And for the direction vector, we can of course take very easily, because we have this vector s, and we know we have to point in that direction. So the obvious choice for the direction vector would be s minus e. We can take any vector on the line, but of course if we take s minus e, then we have the advantage that by t, that was actually I think in the first or in the second tutorial, an exercise, that if we set the parameter t to 0, we get the first vector e. If we set it to 1, we get the second vector s, which is our pixel on the screen. And then we can shoot the ray by just increasing t and making t larger than 1. Now, another thing that we had a couple of times now is that I always said, yeah, it would be much easier if we have a coordinate system where the position where we're starting from, the camera position, is at the origin. And again, I hope you remember that this can be done quite easily. We have, remember for the projective method, we had a gaze vector that gave us our direction in which we are looking at. In this case, we don't have a vector, but we have the screen and we have the camera position, so we can easily calculate that vector by saying it points towards the center of our viewing area. And then let's call that vector w minus w. Then we define a view up vector, which is, I hope you remember, in the plane that you have in front of you, vector pointing up. Then we multiply that with the vector minus w to get a vector u, which is then a vector pointing parallel to the viewing plane, to the right or to the left, depending on in which order we multiply the vectors, in which order we do the cross product of the vectors. And then of course we make the cross product between those two vectors and get a vector v pointing up, and then we have our coordinate system. And yeah, I already said it, depending on in which order we multiply them influences of course if we have a right or a left-handed coordinate system, and also if we choose to look into minus w direction or w direction, because that determines then if we have a right or left-handed coordinate system. What do we have here? Right or left-handed coordinate system? That's easy. Come on. You don't remember? You have to map your fingers to the coordinate axis. So, what do you have here? Right-handed. If you think it's a left-handed, you should see a doctor because your fingers are broken. Good. All right. So, yeah. The other thing we have to do, of course, is to normalize them, because that's another thing that is... you don't know that. The left and the right-handed coordinate system is you have to map your fingers to the coordinate axis, and depending on that, that changes then of if you're looking in a positive or in a negative direction, and that is of course the important when you do the calculation. Good. All right, so we have our coordinate system now. We have it normalized, so we have an orthonormal basis. And now we have a viewing window, and now we want to express, of course, this viewing window in the new coordinate system. So we specify again our viewing window, which like we did it also for the view frustum, with left, right, top and bottom, only not fra and front plane, because here we have a viewing window and not a view frustum. And of course the distance between, we also have to know the distance between the camera and the view window. And if we have that, then we can of course map our window, which has, for example, the size nx and y to this viewing window by this following operation, which normally I would say you all know that, but based on my previous question, I think it's actually a good idea that I have an example here on how to calculate it, because I also realized that from the tutorials that for some people it's very helpful to look at these things with a simple example, which is something that I usually don't do, because I kind of assume that you do this yourself when you look at something and you don't understand it. And I always tell people, yeah, if you don't understand it, just look at the simple example, think about a few, fill in some values and check it. But apparently people don't do that, so I already made a note. Next year I will make more exercise like this in the tutorials also. Unfortunately, you will not benefit from it. I hope you will not benefit from it, because that would mean you would fail the course. Anyway, so yeah, example. So this is how we do the mapping from the NX to the NX and Y to the viewing window. So just a simple example. Let's assume our left side is minus 500 and the right side is 500, and we want to map a window of the size 100 to it. So this is just for the x-axis. For the y-axis, it's the same. It goes in the same way. So we have here from 0 to 100, and we want to map that from L is minus 500 to R is 500. So here we have also we have 1000. So we want to map 100 to 1000. Now if that would be also from 0 to 1000, then this would of course be, so we want to know if we have, for example, here a point at I is 30, where does this point end up here, I dash. If it would be from 0 to 1000 here, then it would of course be easy. It would be 300, and it would be 300 because we would calculate it with R minus L times E divided times I divided by NX. So 1000 divided by 100 times 30 is, of course, 300, which would be the correct solution if we would go from 0 to 1000. But since we are not going from 0 to 1000, we have to add the left side here, which means in this case we're going from, we add minus 500, which means we end up here at minus 200, which is exactly the position that we have here. Is that the right position? Yeah, sorry. I got confused myself. Yeah, that is then of course the right position we have here. Another thing we have to consider always when we're dealing with the pixels is of course that we are dealing with the center of the coordinate system, which is of course why we have to add this 0.5 here. So you see here this mapping illustrates why, or this example illustrates why this is the correct mapping. Now if we have the mapping, then of course we have to shoot our rays in the area where we want to do the projection. Now with the perspective projection, or when we talked about projection, we talked about two kinds of perspective that we have. We have the perspective projection, but we also have the orthographic projection, or the orthographic view, where we do not project towards a camera, but we project towards the viewing plane. So we do not get this perspective that we have in real life, but we have more planar images. And of course we could also do this here. We can do this for ray tracing. We can have perspective projection, but we can also have orthographic projection by shooting our rays not from the center of the camera towards the pixel of the screen, but by starting from the screen and then shooting in exactly this direction in which we would project when we would do an orthographic projection, namely in a direction which is perpendicular to the screen window. And that means the rays all have the same direction, but they have a different origin. But it also means, of course, that the origin is exactly the point that we were just specifying, because that was the point or the pixel position on the screen. So for each direction vector here, or for each ray here, we have a different origin, which is exactly the vector that we specified by u and v. But of course u and v here at this position, so we have to add the I vector e, and then we go up and right based on this where we want to end up at our screen. And this is then the origin, and the direction is of course the value w, because we're minus w. Yeah, I just thought I had a mistake here, but it's correct. It's minus w because we're looking in that direction. And then by a parameter alpha, we can control how far we go on our array, or how we shoot our array. Like I said, if alpha is larger than 1, then it is everything behind the screen. So we're shooting our array into our scene behind the screen. The reason why I have chosen alpha here and not t like before, like we usually do with parametric equations, is that I realized there is a confusion with this parameter t here, but it is just a parameter. I've just chosen another letter for it. Good. And of course, if we want to do the perspective projection, then our arrays look a little bit different, because then our arrays all start at the very same position. They all start at the origin, but they have a different direction, namely the direction from the position of the eye through the pixel on the screen. And we have specified how we can describe this pixel on the screen. We used it just previously in the previous example for getting the different origin. Now we have it to get the different direction vector, and the origin is always the same, namely always the eye position. So you see here the equations look very similar, but they are very different, because here we have this describes our origin, and this is our direction vector d. So if we call this direction vector d, then this is our d, and this is our origin, whereas here this is our origin, and this is our direction vector d. Good. So we know now how to calculate array. We know already how to calculate normals. I'm not going to repeat that, because there is really nothing different here than compared to the previous cases that we had. What we do not know, what you also know, but what I'm going to repeat, because there is something a little bit new, is how do we calculate the intersection. In general, we had this before, of course. If we have a line and a surface that is represented in its implicit form, then calculating the intersection is relatively simple. You just take the principle behind this is simple. The mathematics are sometimes not simple, but we take the parametric representation and just put it into the implicit equation, and then we solve that equation for this parameter that we have in a parametric equation. With this parameter we can then calculate the intersection point. And we had this example for a sphere. I put it down again to repeat, because I'm sure a lot of people have forgotten it. A sphere can be represented in its implicit form in this way. And you probably remember that we showed that based first on a 2D case, where we used the Pythagoras to describe these values here, these equation here, and then we generalized it to the 3D case, and then we also generalized it to from the center of the coordinate system, that the origin is at the center of the coordinate system, that it is at a random point, which is why we have to subtract here this c vector. And or here in vector form, it's actually easier to see. And now if we put in our parametric equation into this, then of course the things looks a little bit more confusing, but we see here that this is the only parameter that we have, the only unknown. Everything else are vectors that are given by either our line equation or our sphere equation. So if we sort this by the vectors, we see that we have a quadratic equation here, and we know that we can solve quadratic equations like this with this formula. And if you do that, if you put them in, then you can calculate the solutions here. And one of the reasons why I want to bring this up again is at that time I asked you what happens if one of those solutions is negative, and then after a while someone came up with the idea that he figured out, okay, that is if you are inside of the object and then looking in one direction, then of course everything behind you is negative if you are placed at the origin. And now of course you know why why we have such situations, because in ray tracing it is you're shooting your ray from your eye, so you have the origin in your eye, and that means everything behind you is negative, and that means of course that this situation can easily happen. Good. Another thing that we already talked about is the intersection of a triangle with array, but this is now a little bit new stuff that I haven't talked about earlier. Earlier we talked mostly about how we check if an intersection point of a plane defined by a triangle is really inside of the triangle or not with the barycentric coordinates, but I didn't really talk much about how to calculate the intersection of course, you can do it in a way that like we do with the sphere. But we at that time when I did this, we didn't have linear equation systems, which is why I didn't bring this method here, which is again the same as we already did, but it's kind of a nice way, on a simple way to do it. If we take the parametric equation and say this should be the same as the equation of the ray, and this should be the same as the equation of the surface. So for example, in this case, the equation of a line, we get 3 different equations with 3 parameters. And yeah, with 3 parameters if we have a parametric representation, because then the surface has 2 parameters, of course. So for the ray triangle intersection, like I said, we talked about how to check if a point is within the triangle, but we first, of course, have to calculate the intersection point. So what we do is we first define the plane that goes through the triangle, and this is again the parametric representation of the plane. Now you probably remember from the tutorials that we had the barycentric coordinates, that we said that the barycentric coordinates actually look pretty similar to the parametric equation of the plane. And in fact, the representation of barycentric coordinates is indeed the same as the representation of a parametric plane, only the other way around. You have to be careful. For example, in the exam for the parametric for the barycentric coordinates question, there were a few people who have chosen different vectors here. They have chosen a minus b instead of b minus a, which would give a correct plane equation, because for the plane equation you just need 2 direction vectors on the plane, but it would give not the right solution for barycentric coordinates, because for the barycentric coordinates you treat this one vertex here as the origin and these 2 as the base vectors, and then you remember this specifies this grid in a similar way as we have normally a grid in the Cartesian coordinate system, only that the grid cells are now parallelograms, so they are twisted a little bit, but that gives us the nice feature that we have here. This vector is from 0 to, for this parameter beta, we can go from this vertex to that vertex, and also gave us this nice condition to check for the 2 parameters what they have to fulfill to make sure if the point that is represented in this form is within the triangle. Now, and that's why, of course, you have to choose the vectors in this way. Now, for the to first calculate this point, we define this plane, the plane in this way, and then we set this plane equal to the line, the ray equation, because of course the point, the intersection point, is on the ray and on the plane. And if we transform that and write this down for each coordinate, we see that this looks pretty much like a linear equation system. It doesn't look pretty much like a linear equation system. It is a linear equation system. And if we look at all the parameters that we have here, we can of course write them in this augmented matrix form. So we have in the matrix form. So we have here the constant values, here the constant values, and these are the parameters. So we can calculate them by solving a linear equation system. Now the interesting thing here is, of course, we do not just get the intersection point, we also get the beta and the gamma that represent this point in the barycentric coordinate system. So by calculating this intersection point, we already have everything calculated that we need to check if this point is inside of the triangle or not, by using these conditions which we used for which are the ones that we use for the barycentric coordinates, because we specified our plane in the same way as we would do the representation in barycentric coordinates. All right. Yeah. So of course we could also do the intersection like we did it with the sphere and the plane, that the sphere and the ray before, that we take the ray equation and put it into the implicit representation of the sphere, and then we get this we can solve for t, because then we only have one parameter there, and then we have the t that we can enter to get the intersection point. But of course, with the other approach, we don't have to calculate the intersection point explicitly if we already know by testing the conditions for beta and gamma that it doesn't intersect with the object. If we have the intersection point, of course, an easy way to check if it intersects with a triangle or in general a polygon is, and I hope you remember that because that was just last lecture 2 days ago that we talked about that, but it's good that it shows up here because someone made me aware last time that there is another special case that I forgot to tell. I told you last time if we want to check if a point is inside a polygon or not, we just shoot a ray in a random direction. Of course, a random direction that in the direction of the polygon. If we shoot it to the left, it's pointless. And then we count the numbers of intersections, and then we see here if it is even, it is outside. If it is odd, then it is inside. That's a very fuzzy ray, but you get the idea. And I said one of the exceptions we have to take care of is, of course, if we shoot our ray in a way that it maps to one of the edges of the polygon, then we just have to do a special treatment. And then after the lecture, someone made me aware that there is also another special case. Any idea? Yeah. From the inside of what? Yeah, exactly, through one of the vertices. It doesn't matter if it's inside or outside, but if we have a situation where we just touch the polygon here, we get one intersection point, but not the second one to exit the polygon. So we have to make sure that this also doesn't happen. So there are these two special cases we have to take care of, but other than that, this is a pretty simple approach to do this. Good. And then, so we know how to calculate the ray, how to calculate the normal, how to calculate the intersection point, how to calculate the normal at this intersection point, and then we just have to put on some color onto it. And the first and the straightforward thing is the one that we already had before, and I'm not going to repeat that because I think this is something you should really know because you did this also in the practicals. This is our very first simplified shading model that we defined at the beginning that already covers ambient shading with a hack version like we learned. Like last time we had this more advanced version of radiosity, but the ambient is just adding a constant factor. Lambertian shading, Phong shading to get these highlight spots here, and also of course the Gouraud interpolation between the vertices where we calculate the color. And then we can do a very simple shading and have our very first simple shading algorithm. Of course, this is now the a more formal but still pseudocode description of it, where we also add, of course, this else statement that if a ray doesn't hit an object, then of course we don't shoot it infinitely, but at some point we just give this pixel the background color. Good. So that's the basic simple shading model, and after the break we will then talk about more advanced shadings in relation to ray tracing.